In this video, we're going to discuss main memory and what goes along with it. So, in main memory, the program has to be brought in from disk and placed within a process appropriately in order for it to be able to run. Main memory and registers are the only storage a CPU can actually access directly. The memory unit only sees a stream of addresses and read requests, or addresses plus data and a write request. We register accessed in one CPU clock cycle or less is how fast it needs to be. Main memory can take many cycles, causing a stall. Sometimes, or most times these days, a cache sits between main memory and CPU registers. Also, we need to provide for protection of memory to ensure that applications don't stomp on each other. So a simple approach is a pair of base and limit registers, and they define a logical address space. The thing about this is the CPU has to check every memory access generated in user mode to be sure it's between the base and the limit. So here, for a process, we'd have a base of 300,040 and a limit of 120,900, and so that would be the rate base for that process. So the way it would work is the CPU would get an address, and it would make sure it was greater than the base. If it's not, we throw an error. If it is, we check to make sure it's less than the limit. If it's not, again, we throw an error. Otherwise, we look at the memory. Programs on disk ready to be brought into memory to execute form an input queue. Without any type of support, they're loaded into address 000. However, it's inconvenient to always have the first process at physical address 0. How can we get around this? Well, there are different address of types that have to be dealt with. We've got symbolic addresses in source code, compiled code addresses, which can be bound to relocatable addresses, for example, 14 bytes from the beginning. Linker or loader will bind relocatable addresses to absolute addresses, and each binding maps one address space to another. So, address binding of instructions and data to memory addresses can happen at 3 different stages. At compile time, if memory location is known beforehand, absolute code can be generated. If memory locations change, you have to recompile your code. Load time is another option. We can generate relocatable code if the memory location is not known at compile time. And execution time. Binding is delayed until runtime, and if the process can be moved, it might be from one segment to another. Now for this, we'll need hardware support, such as base and limit registers and other alternatives. So, dealing with a multi-step processing of a program, we've got our source code, then we compile it. We get an object model and other object models, we link them all together to produce a load module, which is then loaded by the loader. Any dynamic libraries are loaded, and from there it can be executed. One of the things we need to talk about is logical versus physical address space. A logical address is bound to a separate physical address space, and it is necessary to think like this for proper memory management. A logical address is generated by the CPU and can also be known as a virtual address. A physical address is actually the address in a memory unit. In compile time and load time address binding, logical and physical addresses appear to be the same. In virtual, and the difference is logical and physical addressing schemes differ in execution time address binding schemes. A logical address space is the set of all logical addresses generated by a program. A physical address space is the set of all physical addresses generated by a program. Remember, because of our 3 options, those 2 might not be the same. A memory management unit is a hardware device that maps virtual to physical addresses. There's a whole bunch of different types of that, which we'll talk about. But consider a simple scheme where the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. The base register can now be thought of as the relocation register. With MS-DOS, the Intel 8086 used 4 relocation registers. The user program deals with logical addresses, okay? Just like in your toy operating system, you have to deal with logical, not physical addresses. It never sees the real physical address. Execution time binding occurs when reference is made to a location in memory, and the logical address is bound to a physical address then. So using a relocation register, here's a way to deal with it. A routine isn't loaded until it's called. It has better memory space utilization. Unused routines are never loaded. All routines are kept on disk in relocatable format. And it's useful when large amounts of code are needed to handle infrequent cases. It doesn't really require much special support from the operating system. Your program can usually help this. The OS can use help by providing dynamic link libraries. So here we have logical address 1346. Our relocation register would be 14,000, and the MMU would add them together and get us to the actual physical register location. So dynamic linking is an important concept. Static linking is when system libraries and permanent code are combined to a complete image. Dynamic linking is postponed until execution time. A small piece of code called a stub is used to locate the appropriate memory resident library routine. When it's loaded, the stub replaces itself with the address of the actual routine and executes the routine. The operating system checks to see if in-process's memory address contains the routine. If not, the address needs to be added to the address space. Dynamic linking is particularly useful for libraries. Systems are also known as shared libraries. Versioning may be needed, and patching is important too. Windows uses what's called dynamic link libraries, and there's a concept called DLL hell, which basically is versioning can become a nightmare. So, swapping. A process can be temporarily swapped out of memory to a backing store, such as a hard drive, and brought into memory to continue execution. Therefore, the total physical memory space of the processes can exceed the physical memory space. This is the example we're using in our project. Okay. Backing storage should be fast enough to accommodate copies of all memory images and make it reasonably quick to bring them in. There are definite variants of algorithms for this. There's a swapping variant called roll in, roll out for low priority based scheduling. A low priority process is swapped out, so a higher priority process can be loaded and executed. The major part of swap time is transfer time. Total transfer time is directly proportional to the amounts being swapped. The system maintains a ready queue of ready-to-run processes which have memory images on disk and can load them in as needed. So, a question. Does the swapped-out process need to swap back into the same same address? Depends on the binding method. Also, if you have pending I/O. Modified versions of swapping are found on Unix, Linux, and almost Windows and almost everything else. Swapping can be disabled, but it's started when you start running out of memory. And it can be disabled once you go below a threshold. On my machine, for example, there is something called the Windows swap file. But similarly, on my machine, it's almost never used because I have 128 gig of RAM. So it's pretty rare that I have more programs in memory than can be used, so it's not needed. So here's one way to look at it from a schematic point of view. The operating system swaps out a process, PI, and pops in a new one from the backing store, and we continue on our merry way. So when you do swapping, you have to worry about context switching time. If the next process to be put on CPU is not in memory, we need to swap out a process and swap in a target process. So that could make it very expensive. 100 megabyte process swapping to hard disk with transfer rates of 50 megabits per second will take 2,000 milliseconds to swap out, plus swapping the same side process, leaving us 4 seconds. We can reduce this if we know the size of memory is actually really being used. You can use request memory and release memory for this in Linux. There are other constraints as well. You can't swap as long as pending I/O is occurring because it would return to the wrong process. So, or you have to transfer the I/O to the kernel space and then back to the new device. This is called double buffering, and it adds overhead. Standard swapping is almost never used in modern operating systems. We use modified versions of it or different approaches. We swap only when memory is extremely low, and at that point you should be noticing enough performance that you'll probably go in and kill some processes. Swapping isn't typically supported on mobile systems. The amount of memory is usually small, you only have a limited number of write cycles, and you get 4 throughput. Instead, in iOS, for example, it asks these processes to relinquish memory, and then any read-only data can be thrown out and reloaded if needed. If they can't free up enough memory, you could have a termination. Android terminates apps if low memory, but first it writes an application to flash for a fast restart. So it's not quite the same as swapping. A main memory must support both operating system and user processes. Limited resources must allocate efficiently. An early method was contiguous allocation. Main memory usually into 2 partitions, the OS usually held in low memory with an interrupt vector, and processes then held in high memory, each process contained in a single contiguous section of memory. Relocation registers were used to protect processes from each other and from changing operating system code and data. The base register contains value of the smallest physical address. Limit registers contains a range of logical addresses. The MMU maps logical addresses dynamically. You can then allow actions such as kernel code being transit and the kernel changing size. So again, like before, we'd have the same process, but this time it's hardware based. Another later approach is a multiple partition allocation scheme, and the degree of multiprogramming is limited by the number of partitions. Variable partition size can be used for efficiency, but this can leave you with holes. When a process arrives, it's allocated memory from a hole large enough, but you have to be careful because eventually you will start ending up with holes that are too small to be useful. So the problem is how to satisfy a request of size n from a list of free holes. Well, there's the first fit, allocate the first hole. There's best fit, allocate the smallest hole that's big enough. It requires us to search the entire list unless we order it by size. This produces the smallest leftover hole. There's also worst fit. Allocate the largest hole, you have to search the entire list, and it serves the largest leftover hole. Worst fit obviously performs the worst. Now what happens is we get into what's called fragmentation. Total memory space exists to satisfy our request, but it's not contiguous, so we can't use it. So internal fabrication, allocated memory might be slightly larger than requested memory, and this memory is internal to a partition but not being used. First fit analysis reveals that n blocks allocated, 0.5 blocks are lost to fragmentation. So up to 1/3 might be unusable. We can reduce this by doing what's called compaction. We shuffle memory contents to place all free blocks together in one large block, but it's only possible if relocation is dynamic and it can be done at execution time. Again, we've still got to latch our job in memory when the I/O is involved, and we also have to deal with the same problem on the backing store. So there's another approach called segmentation. With segmentation, we have a memory management scheme that supports the user view of memory. Consider a program. It's a collection of logical units such as main program, procedure, function, method, object, local variables, global variables, common blocks, stacks, symbol tables, and arrays. There's a lot to it. Okay. The user looks at a logical address space having all these things: a subroutine, symbol table, stack, etc. Now, this can be mapped into memory in these blocks. Like block 1 would be whatever, stack. Block 2 would be, I don't know, program data or a method. All these can be mapped to physical space. So now, a logic address is a two-tuple. It's a segment number and an offset. We will also have a segment table, which maps two-dimensional physical addresses. Each entry has a base, where it starts in memory, and a limit, the size of the segment or length. A segment table base register points to the segment table's location in memory. We have to store that as well. So, and there's also a length register, and it indicates the number of segments used by a program. A segment number S is legal if S is less than the segment table length register. We can use this to implement protection. With each entry in a segment table, associate a validation bit, which determines 0 being an illegal segment, and a read-write execution privilege set. Protection bits associated with segments allow code sharing to occur at the segment level. Since segments vary in length, memory allocation is a dynamic storage allocation problem. A segment example is shown below. Here we've got a CPU, we've got our segment and our offset. All right. So when we try to read memory, is the offset less than the limit and plus base? Yes. Then we get to our memory by adding the base to it. No, otherwise we get an error. So another way to approach this is by paging. This is when physical address space of a process can be non-contiguous. A process is allocated memory whenever the latter is available. This avoids external fragmentation and varying size memory chunks. So what we do is we divide physical memory into fixed size blocks called frames. Typically the size is the power of 2, which is a good idea because of the way drives are organized, and between 512 bytes and 16 megabytes. It's dependent on your implementation. Then we divide logical memory into blocks of the same size called pages. Remember, frames are physical, pages are virtual. We keep track of all of our free frames, all of our free actual memory. To run a program of size n pages, we need to find n free frames and load the program. So we set up a page table to translate logical to physical addresses. Again, the backing store is typically split into pages. You can still have internal fragmentation, though, but it's much less likely. So our address translation scheme is as follows. An address generated by the CPU is divided into a page number, uses an index into a page table, which contains a base address of each page, and a page offset, which combine with the base address to define the physical memory location. So for a given logical address space of 2M and a page size 2N, we can appropriately determine where in memory it is. And this would give us the size of our page table as well. M would be our page table with size n. Some CPUs have paging hardware. You have a CPU with a frame location and a page location and an offset that would look up in our page table, which would give us a frame location and an offset, which would lead us to physical memory. So here's how it could look in memory. In logical memory, you've got page 0, 1, 2, 3, 4, right? But the way it could be laid out in the page table is 0, 4, 3, 7, based on how it was located. So our page 0 here would be frame 1 here, page 1 here would be frame 4 here, and so on. So here's a paging example with n equals 2 and m equals 4, 32-byte memory and a 4-byte pages. So here is our logical memory in pages. got A, B, C, D, blah, 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 etc. And here we've got page 0, which points to frame 5, which I am blind and cannot see. Sorry, here we go. We've got pages. Here we've got logical memory organized into pages, and there are 4 pages starting from 0. We have a page table which says 0 points to block 5, 1 points to block 6, page 2 points to, frame 1, and page 3 points to frame 2. So here's 0, 1, 2, 3, 4, 1, 2, 3, 4, 5. You'll have to forgive me, there's an actual extra frame in here, so let's just ignore the first one. So 0 is at frame 5, 1, 2, 3, 4, 5. 1 is at 6. 2, which is this guy, would be at 1. And 3, which is this guy, would be at 2. Notice no dependency on actual location. So how do we calculate internal fragmentation? We've got a page size of 2K, a process size of 72K approximately. That gives us 35 pages plus 1,086 bytes. So our fragmentation would be 962 bytes. Our worst case would be one frame contains 1 byte. The average would be half a frame size, which this example shows. So are small frames desirable? But the problem with small frames is each page table takes memory to track. So the page sizes end up growing, which often leads to having to grow the page sizes over time. So Laris, for example, supports 2 page sizes. By doing this, though, this approach, process view and physical memory are now very different. But when you implement it, a process should only be able to access its own memory. So the process must also track the list of pages associated with it. So let's take a look. Here we've got our free frame list before allocation, right? We've got 13, 14, 18, 20, and 15 are all free. We've got our new process containing 3 pages, right? We're going to fill in the pages appropriately by using a process page table, right? So we've got page 0 here corresponding to page frame 14. We got 1 for corresponding to 13th, and so on and so forth. But notice this is a page table associated with the process. So how do we implement this? The page table is kept in main memory. A page table base register points to the page table. The length register indicates the size of the page table. Every data and instruction address requires 2 memory accesses, 1 for the page table and 1 for the data and instruction. The 2 memory access problem can be solved by use of a special fast lookup hardware cache called associative memory, or TLB, translation look-aside buffers. But that's a hardware question for your hardware architecture class, not this one. Some top-level transition look-ahead buffers store address space identifiers in each entry, uniquely identifying each process to provide address space protection for that process. So that's a different approach. Instead of having each process have its own tables, you could actually just tag various pages within memory as associated with a process. But those would have to be swapped out and swapped back in. The TLBs are typically small. We keep trying to 60 to 1024 entries. On a miss, the value is loaded into the TLB for fast access next time. Replacement policies must be considered. You can lock some entries down for faster access. A source of memory is a parallel search. Instead of searching one memory at a time, it searches all of them at once. However, it is considerably more expensive. So, associative memory is literally searched in parallel, but it's very expensive. Address translation can be simplified a little bit because if it's in the associative register, get the frame number out. Otherwise, we're going to have to use the frame table. So this, it looks a little bit more like this. We've got our logical address. We've got our TLBs with a page number, frame number. If we hit it, that's good, and we can go right down to memory. If not, we are going to have to go to our page table. So, for effective access time, the associative lookup can be less than 10% of memory access time. Let's call our hit ratio alpha, and consider alpha equal 80, epsilon time unit, 20 nanoseconds for a TLB search. So our effective access time is computed below. And so if you look at 120 nanoseconds, that's a tenth of a second, which could be expensive given enough accesses. So on to memory protection. Memory protection implemented by associating a protection bit with each frame to indicate if it's read-only, write-only, or read-only or a read-write. We can also add more bits to indicate if pages execute only and so on, a way to protect program memory. There is a valid, invalid bit attached to each entry in the page table. Valid indicates the associated page is in the process logical address space and is thus legal. Invalid indicates the page is not in the process logical address space, or we can use the page table link register. Any violations of this would result in a trap. So here's an example of laying out the valid and invalid bits. And for example, if we look at 5, we can see the actual frame is not in memory. If we look at 6 and 7, I'm sorry, if we look at 6, it's also not in memory. The valid ones are. Oh, but these are counting from 0, by the way. Sorry, I keep misreading these documents. How about when we have shared code? One copy of read-only code, reentrant, meaning two systems can access it at the same time without risk, is shared among processes. It's similar to multi-threads sharing the same address space. It can also be used for inter-process communication if sharing of read-write pages is allowed. Each process keeps a separate copy of, otherwise each process could keep a separate copy, and the pages could be anywhere in the logical address space. That does reduce some of the effectiveness. So here we have process and a page table for the process. And here we'd have the shared memory, and that would be accessible by all three appropriately. So memory structures for paging can get huge using straightforward methods. If we've got 32-bit logical address spaces and a page size of 4K, we'd have over 1 million entries. Some ways around this are hierarchical paging, hashed page tables, or inverted. Hierarchical page tables is basically creating a 2-level page table. So we'd look in here first, and then there, and then there. So we now have a 3-tuple for each piece. So a 32-bit address would be divided into a page number. A logical address would be a page number and an offset. Since it's page, we'd further divide that into 3 pieces. And our address translation scheme would be an outer page table back to the page of a page table, and so forth. However, for a 64-bit logical address space, that gets even more out of control. So it could take up to 4 memory accesses to get 1 page. Another option is in systems with address spaces greater than 32, the virtual page number is hashed into a page table. The table contains a chain of elements hashing to the same location. Very similar to just data structure hashing. Each element contains the virtual page number, the value of the map page frame, and a pointer to the next element. Virtual page numbers are then compared. So basically, this is like open hashing. We could also cluster them as well and could use this for sparse addressing. But here's an example. We've got our hash function, which gets us into our hash table, which gets us our actual our hash into the appropriate address in the hash table entries, which are followed by the next hash table entry. So we find our actual page and our index, and we get to our physical memory. So rather than each process having a page table and keeping track of all possible pages, we could track all physical pages with one entry for each real page. An entry consists of the virtual address of the page stored in that real memory location with information about the process that owns that page. It decreases the memory needed to store each page table, but increases the time to search the table when a page reference occurs. You can use a hash table to limit the search entries to one or at most a few page table entries. But how to implement shared memory? One mapping of a virtual address to the shared physical address. But here would be the actual architecture. Again, we'd have a logical address. We'd search our page table to get our frame, and that would lead us to physical memory. So here are some details from Intel. Intel is still dominant. Many variations in the chip cover the main ideas here. There's all sorts of them. The IA32 architecture, which is also known as Itanium, I believe. Each segment can be 4 gigabytes. That's pretty big segments. And you can also have segmentation with paging. Each segment can be 4 up to 16K segments per process. 16,000 segments per process. It can be divided into 2 partitions. The first partition of up to 8K segments are private to a process. The second partition are shared among all processes and kept in a global descriptor table. So the selector given a segmentation unit which produces a linear address. The linear address is then given to a page unit which generates a physical address. And here's more details into how it actually works. However, 32-bits can create a page address extension, which is a 3-level scheme. These days, the x86 doesn't have to use that. It's huge, but typically only about 48 bits of it are actually used. But you could use it if you want, so you have almost unlimited memory. We're going to skip over the ARM architecture, but that's the basics of physical memory.